Okay, so looking at question number 6, it says a block of mass 2 kilograms and an initial speed of 34 meters per second slides on a rough horizontal surface and is eventually brought to rest after traveling a distance of 4 meters. Calculate the frictional force between the block and the surface. So let's draw our picture for what's going on here. If this is our surface, and again, we have a rough surface, so there is friction that's acting. And I'm just going to have it here initially with an it's a 2 kilogram mass, and it is moving to the right. So it has some velocity. It has some velocity, initial velocity equal to, what was that, 5.4. Slides on a horizontal rough surface and eventually brought to rest. So after some distance, our object sits here, and now our final velocity is equal to 0. And that occurs over a displacement s equals 4 meters. So it says calculate the frictional force between the block and the surface. And a few different ways, well, I guess there's not really a few different ways that we could do this, but let's first think about our block, right? And think about, okay, what are the forces acting? So we have the force of gravity down. We have, that's our weight, we have our normal force up, and then we're gonna have a frictional force to the left. And there's nothing pushing it to the right, it's just sliding that way, so that's the direction of its motion, but the force is to the left. And so if we were to do our net force equations, the forces in the x direction would just be a negative force of friction. There we go, negative force of friction equals mass times acceleration in the x. And then our sum of the forces in the y are going to be normal force minus the force of gravity equals mass times acceleration in the y. And we know that this would be 0. And so this tells us that our normal force equals our force of gravity. So we're going to be accelerating to the left. I hope that makes sense, because with an acceleration to the left and a movement to the right, we're going to slow down. And again, our acceleration has to point in the direction of our net force. These two forces are the same. Frictional force is an unbalanced force. There's no other force pushing to balance it out. And so that's our unbalanced force, that's our net force, and it's to the left. So when we deal with this, with work and energy, we're trying to find the force of friction. What we need to understand is that initially our box has some kinetic energy. It has a velocity greater than 0, so it has kinetic energy. Whereas here, our kinetic energy is going to equal 0. So we have a kinetic energy greater than 0, and then we have a kinetic energy equal to 0. And what we can say is that the work net is going to cause a change in kinetic energy. And we know that work, so here's kind of equation 1. And equation 2 is the idea that work equals force times displacement cosine theta. All right. Well, if we think about this, if my displacement is to the right, that's my s, the angle here, right, that would be my theta of basically 180 degrees. And that's just going to mean that I have negative work done. So this I know is going to eventually be -1, or excuse me, the angle itself is 180. However, the cosine of 180 is going to be -1. So let's put this together. Let's find the force of friction and understand this. So the work done by friction is going to be the force done by friction times the displacement times -1. And we know the displacement, that's s, that's 4. We don't know the force of friction, but we can use equation 1 to solve for my force of friction, or determine my work done. So using equation 1, what that shows is work equals the kinetic energy final minus the kinetic energy initial. That's going to be the 1/2 mv, v squared minus 1/2 mu squared, right? So this is my initial velocity, or excuse me, initial velocity. This is my final velocity. So what we can see is that my final velocity is 0. So that makes this entire portion of this 0, which then the work is going to equal negative 1/2 m initial velocity squared. So that's how I'm going to use this first equation here. My second equation builds here. And then what I know is that the work is the work done by friction. So I can put these two equations together there. So I'm going to get that the force of friction times the displacement times -1 is going to equal the work done, which is -1/2 mu squared. And then solving for my force of friction, I'm going to divide each side by basically -s. And that would cancel out my displacements here on the left. And I'd be left, as well as my negative, and I'd be left with the force of friction equals 1/2 m initial velocity squared over s. Or another way to write that would be m initial velocity squared over 2s, right? And now I just got to plug in the values that I know, right? So with this, that's going to equal a mass of 2. My initial velocity is 5.4 squared divided by 2, and my displacement, again, is 4. Plug that in my calculator, and I should get a value for my force of friction of 7.29 or 7.3 newtons. So again, walking through this question, right? We know our initial object has kinetic energy. We know the final has 0 kinetic energy. So the change in kinetic energy is simply whatever I had to start with, right? But it's a negative because that's how much energy I lost. And I lost that because friction was acting opposite the direction of its motion, and that's going to cause some of kinetic energy to turn into thermal energy. And so if I know that work causes a change in kinetic energy, and I also know that work is force times distance cosine theta, I can plug those two equations together, and that's how I solved for my force of friction there. And again, 7.29 newtons.